A triangle is a three-sided figure having three corresponding angles. The sum of the angles is always 180 degrees. Angles less than 90 degrees are called acute, and angles greater than 90 degrees are called obtuse. A triangle may have one obtuse angle, but always has two or three acute angles. Each angle is formed by two adjacent sides, and each angle has one opposite side. Angles are labeled uppercase ABC, and sides are labeled lowercase ABC. Notice the correspondence between each angle and its opposite side. If all three sides are the same length, the triangle is called equilateral. Sides doesn't matter as long as the sides remain equal. Equilateral triangles always have 60-degree angles. If two sides are the same length, the triangle is called isosceles. The two corresponding angles will always have the same measure, but that measure may vary as overall proportions vary. If one angle is 90 degrees, it's a right triangle, as denoted with a square indicator. The side opposite the right angle is called the hypotenuse. Sides adjacent to the right angle are sometimes referred to as legs. If both legs are the same length, it's an isosceles right triangle. The acute angles in an isosceles right triangle are always 45 degrees. If we adjust the length of one leg to 3 and stretch the other to 4, the hypotenuse will have a length of 5, hence the name 3-4-5 right triangle. If the measure of one acute angle is 30 degrees, the other will be 60 degrees, hence the name 30-60-90 triangle. Since angles in any triangle always add up to 180 degrees, if the measure of two angles is known, the third can be calculated using simple subtraction. But what if you know the length of two sides and want to know the third? If it's a right triangle, you could use the Pythagorean Theorem.
In a right triangle, the square of the hypotenuse is equal to the sum of the squares of the legs.
Here's another way of looking at it. C squared is equal to A squared plus B squared. What's that mean? Earlier we labeled sides as ABC, making sure sides corresponded to angles. Other than that, we really didn't care which letter was assigned to which side. But the Pythagorean theorem only works with right triangles, and when dealing with right triangles, particular attention is always paid to the hypotenuse. For the Pythagorean theorem to work, the hypotenuse must be labeled C. It doesn't matter which leg is labeled A or B. With this in mind, let's take another look at the Pythagorean theorem and see if it makes more sense. In a right triangle, the square of the hypotenuse is equal to the sum of the squares of the legs. For example, suppose we know the length of a triangle's legs and want to determine the length of the hypotenuse. We'll plug our known values into the equation. Next, they're squared, which just means you multiply each number by itself. Those intermediate results are added together. To finalize the calculation, we'll take the square root of both sides of the equation, yielding the length of the hypotenuse. Let's take another look at that equation. This time, let's take the square root while the equation still consists of only variables. Just like before, we'll take the square root of both sides. The reason we're taking the square root is to strip the exponent off of c right from the beginning. Now we'll continue the calculation using the modified equation. Substitution of known values occurs just like before, except that this time the square root radical appears on one side of the equation right from the beginning. Squaring known values produces the same result, as does adding those squared values together. You can see that the calculation is similar whether the square root radical is introduced in the beginning or the exponent on c is carried through. It was at this point that we introduced the radical before, but this time we've already done that up front. Either way, we eventually arrive at the same answer. What if instead of knowing the length of two legs and wanting to determine the length of the hypotenuse, you know the length of the hypotenuse in one leg and want to know the length of the other leg? In our example, we want to figure out the length of side A. Before plugging in our length values, we'll massage the equation a little. Previously, c was all by itself on one side of the equal sign. But now, we want to solve for a, meaning that a needs to be all alone. There's a little trick in algebra that lets you do that. We're going to subtract b squared from both sides of the equal sign. Because we're operating evenly, the algebra police won't come after us. On the right side of the equation, plus b squared and minus b squared cancel each other out. That leaves a squared by itself, which is exactly what we want. Again, we'll take the square root of both sides of the equation before plugging in known values. That strips the exponent off of a, which completes our work with only variables. Now that the equation has been tweaked, we're ready to plug in our actual values. The remaining steps are the same as before, except that known values are subtracted instead of added after they're squared. Solving for the other missing leg is identical, except for variable assignment. Regardless of which leg we're solving, we're going to start out with c squared is equal to a squared plus b squared. When solving for a, b squared was subtracted from both sides of the equation. The goal was to cancel out plus b squared so that a squared was left alone on one side of the equal sign. Solving for b does the reverse by subtracting a squared in order to cancel plus a squared and isolate b squared. Either way, the next step is to take the square root of both sides of the equation. Taking the square root of a squared term has the effect of stripping off the exponent. Since it's nice to have the isolated term on the left of the equation, I'll flip everything around. I'm using an unorthodox technique to save 3 more algebra steps because my head already feels like it's swimming in alphabet soup. Maybe it's easier to forget the algebra and just remember these steps. Start by identifying which triangle part you're trying to figure out, hypotenuse or a leg. Square both known values. If you're missing the hypotenuse, add the squared lengths together. If you're missing a leg, subtract the smaller squared length from the larger. Finish by taking the square root of that. Let's bring back the isosceles right triangle. We know the length of both legs is the same. We'll assign a unit length of 1 to each. If the length of each leg is 1, what would be the length of the hypotenuse? We'll try the simplified procedure this time. Let's start by squaring the 2 known values. Since we're trying to figure out the hypotenuse, we'll add them together. Don't forget to take the square root of that. When you multiply 1 by itself, the result is still 1, so our squared values look the same as the original lengths. Now we'll perform the addition. To finish, we want to take the square root. But the square root of 2 is an irrational number, so it's often customary to leave the square root radical on the final answer. Now it's time to take a closer look at the 30, 60, 90 triangle. Obviously, if you double the measure of the 30-degree angle, the result is 60. One side is also double the length of another. I'll assign a unit length of 1 to the shortest side, opposite the 30-degree angle. Since the 60-degree angle has twice the measure of 30, you may think the side opposite the 60-degree angle is twice as long as the side opposite the 30-degree angle. But that's not the case. It's actually the hypotenuse that's twice as long as the side opposite the 30-degree angle. So what is the length of the other leg, the one opposite the 60-degree angle? It's time for you to try to figure it out yourself. Remember our 3-step procedure. Square both known values, add or subtract those squared values depending on which length is missing. If you're trying to solve for a missing hypotenuse, you add those squared values together. If you're trying to solve for a missing leg, you subtract the smaller squared number from the larger one. You finish by taking the square root of that. Keep those steps in mind as you try to solve the longer leg of a 30, 60, 90 triangle. You may pause the video now. No cheating. Did you at least give it a try? Step 1 was to square both known values, in this case 2 and 1. Since we're trying to figure out a missing leg, our calculation involves subtraction. Step 3 says we should throw a square root radical around the whole thing. Once our values are squared, we get 4 and 1. After you subtract those squared values, the intermediate result is 3. But if you try to take the square root of 3, you get another one of those messy, irrational numbers. So we'll leave the radical on and express our result as square root of 3. This has been a Now Gene Says production.